Hello, and welcome to Data and AI Summit. My name is Rohit Mathews, and together with my co-presenter, Neo, we'll be talking about what a federated data analytics platform is, why we built one at Databricks, and why it might be the right fit for your organization. Let me take you back to 2001. An engineer named Paul Buchheit was working on a small side project, a web-based email client. The goal, just to be able to search through his old emails. Nothing too fancy or ambitious. It was a quiet attempt to solve a problem that he was facing daily. But when his coworkers started using it, something amazing happened. They loved it. They wanted more. They wanted it to be faster. They wanted better storage. They wanted better threading. And just like that, Paul's little side project became Gmail, a tool that redefines how we think about emails. But why am I talking to you about Gmail at a talk about data pipelines? Raise your hands if you've ever been part of a team putting together an ETL pipeline or a reporting stack. Phew, at least I'm in the right conference room this time. All right. Now, keep your hands up if you worked on it for, let's say, 3 months. Okay. How about a whole year or 2? Adding new features, augmenting it, tracking new metrics. Great. Neo and I need your CVs. Please leave it with us, because you might have built the Gmail of ETL pipelines. Because just like Gmail, a successful ETL pipeline never really stays small. People always want more from it. And Databricks was no exception to this. Stakeholders always wanted more. Some background. Here at Databricks, one of our core principles is to let the data decide. More than any other company that I've worked for, Databricks strongly believes in removing the guesswork out of decision making. I mean, we A/B tested which A/B test framework we want to use. To that end, a team of specialists at Databricks put together a proof of concept pipeline with the goal of answering the question, what if I wanted to know the adoption and usage of every product that Databricks ships and every single product capability within? At Databricks, that meant instrumenting over 1,500 different product capabilities across hundreds of microservices interacting in a complex and nuanced fashion. The proof of concept pipeline generated a table that did just that. Let's take a look at a couple of examples. Meet Anthony. By the way, this is what ChatGPT thinks a member of the finance team at Databricks looks like. Anthony wants to understand the evolution of usage of a set of SKUs, Databricks Delta, Delta Live tables, and streaming. He also wants to understand the weekly active users associated with the same. Then there's Miranda, a product manager for the SQL Gateway team. We all have a Miranda at our company. Her questions are never that simple. Miranda's team has just launched the ability to schedule SQL queries using the job service. And she wants to understand adoption of this new product capability. Ideally, she would like this data broken down by serverless and non-serverless. And she's only interested in those jobs that have processed at least 30 gigabytes of data. No weekend hobby jobs need apply. To answer Miranda's question, we need to be able to reconstruct the lifecycle of a workload from logs of hundreds of microservices, figuring out what services were involved, in what order, and how they interacted with each other. Databricks customers run about 500 million unique workloads on Databricks daily. This means combing through about 1 petabyte of logs to answer that question, each one contributing a small but important part of the full picture. If there was a question you had spanning any combination of the hundreds of microservices at Databricks, The table generated by this proof of concept pipeline was built with the vision of answering it. And just like Gmail, since inception, this table gained massive traction at the company. Today, this table acts as a single source of truth for numerous use cases, including sales compensation, revenue forecasting, abuse detection, and much more. It can provide adoption metrics on it can provide key insights on adoption metrics, like daily active users or weekly active users associated with a newly launched product capability, the number of new workspaces using a product on any given week, or the percentage of revenue associated with any product line. Most organizations facing hypergrowth the way Databricks did pivot in one of two different directions at this point. They either empower their product teams to build their own ETL pipelines, or they hire an army of data engineers to constantly onboard new metrics to this platform. The former approach leaves you with siloed data sets that are hard to reconcile, and the latter just doesn't scale. The pipeline at Databricks was headed down a combination of these two paths. I'm here to tell you the story of how we were able to pivot to power this table using an army of exactly one data engineer. The key was to adopt a platform mindset to hyperscale. But it wasn't always this rosy. Let me take you back 1.5 years to when this table was powered by the proof of concept pipeline. First, it took 48 hours after the end of a business day to generate insights for that business day. Okay, it meant teams couldn't react quickly to changes in trends. Second, performance was deteriorating rapidly. Jobs that were once taking 5 hours now took a staggering 15 hours or more just from organic growth in data volumes. More on the details of this later. I should also note that we had strict SLAs around data freshness for all the tables at Databricks. Anytime a table was not delivered in a timely fashion, it was counted as downtime. This table then had time of only about 50%. No surprises here. If a 15-hour job fails at the 14-hour mark, you have set your pipeline behind by at least 14 hours, and that is assuming the job succeeds at all. On top of that, the metrics from the reporting pipeline had an error margin of about 5 to 15%. This was on account of the complexity of cross-referencing logs from these hundreds of microservices. Again, more on that later. Yet, despite these limitations, this table had gained massive traction at the company. It was answering so many valuable questions that people couldn't wait to onboard instrumenting their platform capability onto it. The only real bottleneck, data engineering resources to keep up with the demand. So that's where we started. Delayed insights, long runtimes, unreliable uptime, and a rising demand that far outpaced our ability to scale. In the coming slides, Neo and I will talk about how we used a platform mindset to hyperscale this platform from a proof of concept to a truly robust self-service and federated platform. As we progressed, we saw monumental improvements across the board. We went from a pipeline supporting 100 metrics to over 1,200. Our system uptime skyrocketed from a mere 50% to a robust 99.9%. The pipeline runtime, end-to-end, decreased from 24 hours to just under 6 hours. Our largest job, the one that I told you took 15 hours, was now completing in less than 1 hour. All these changes led to a substantial 90% cost savings. And the best part, it didn't take an army of data engineers. It just took the right mindset and one data engineer. These metrics aren't just numbers. They represent a transformation, one that fostered a true data-driven culture at Databricks. I would now like to invite my colleague Neo to kick off what our journey looked like.
All right. At this moment, you might be wondering, what could be resulting in this issue? Let's look deeper into the product architectural diagram that we put together after reviewing the code. So here is what we discovered. The POC pipeline was indeed a proof of concept pipeline. The team had built exactly what the stakeholder was looking for, but not in a way that was meant to stand the test of time. The job didn't scale as expected. Doubling the compute resource didn't really double the speed. In fact, a 2x in data volume increase would cause a 4x in the job runtime slowdown. Meanwhile, the data team felt huge pressure. The pipeline got massive adoption that we didn't expect, but it was built by a specialist team that disconnected from the product team. The product team could just go and change the content or the schema of their logs at any time and pull the rug out from under us at any time. The incentive were clearly not aligned. Let's get serious for a moment. The architecture we inherited was a beast. 65 different jobs written in PySpark, Scala, SQL. We jumped in just in time. Any later, we'll be dealing with business logic written in R, or even worse, Perl. Each job cross-referencing logs from various or product services, transforming that raw data into over 100 intermediate tables before delivering this gold table that everybody reads from. At this point, we knew it was time to roll up our sleeves and apply some standard data engineering magic. With the goal of improving the uptime, we applied this classic data engineering playbook. First, we introduced dev and staging environments. This let us launch change safely and spot issue early. Next, we automate all the job batching and backfills. Instead of running a year-long job in one go, we break it up into smaller rolling window, something like a month or 15 days at a time. Next, we made sure that all the tables were optimized before the downstream job touched the data. We reduced the unit failure by having each job write to at most one table. That way, if a job failed, we would have lesser time lost by retrying the same. Last but not least, we put everything under source control and Databricks Terraform provider so that we always knew what changed and when. But here's the key point. You don't want to reinvent the wheel and apply this best practice by hand for each of the jobs. That solution doesn't scale, and it's easy for things to fall through the crack. What you need is a platform mindset, a way to package all this best practice into a standard container that can be reused across every job. That way, all the new pipeline benefit from the same reliability right off the blocks. This change, along with this platform-first approach, made a real difference. With them in place, the uptime of our pipeline shoot up from 50% to 90%. All right, so we have a dramatic shift in the pipeline uptime, but the job was still very slow, and the business logic was still very complex. Why? Let me try to answer it. But before that, let's do another quick poll. How many people think of measurement in terms of kilometer and centimeter? No. Great. A lot of engineers around the world. How many people think of measurement in terms of inches and feet? Looks like we got some fans of Home Depot and in-home project, DIY project at home. How many people think of measurement in terms of nanometer? Great. You guys are in the wrong conference room. The nanotech talk is two blocks down the street, and also you're here early by about 2 weeks. People think differently. And that's exactly what happened when teams are generating their logs. Looking at the logs emitted by teams is like looking at the data collected in Celsius, Fahrenheit, meters, miles per gallon, or whatever other combination you can think of. Teams are not speaking the same language and semantics, and cross-referencing that logs require building complex heuristic logic that is difficult to comprehend in the best case and easy to break in the worst case scenario. At this point, you probably want to know what that expression could be. This, believe it or not, is a simplified version of what the join clause look like when cross-referencing the logs. When we try to stitch logs together, the code turns into a mess of substring and regex expression. Honestly, don't bother trying to read it. The point is, this mess was everywhere. Over 60 files packed with this messy logic, chaotic, but not without purpose. But you might be wondering why it gets so messy in the first place. Let me break it down with a real example. Imagine the user kick off a workflow in Databricks. The job service emits logs and tag them with a job ID, let's say job 123. Then they hand off to service A, which logs using its own ID. Then the service B jumped in, managed by the techiest team at Databricks, whose ID are cryptic, something like Spark 487 123 attempt 2. Well, it has a start to tail, and it wants to leave no ambiguity. Finally, the service C enters into the picture. It emits logs too, but with no tag or context that trying back to the original workflow. This log became orphan logs, impossible to trace back to where it came from. When it's time to actually connect the dots, we end up with this messy logic. This is an actual screenshot of the cross-referencing logic in action. As a data engineer, the minute you see a substring and regex expression in a join, you know you are in deep trouble. If you see a combination of substring, regex expression, coalesce, you know for certain that you can put together a 5-course meal between the 2-round testing of your same code. If you are looking at the Spark UI and trying to figure out where the data skew came from, you are not doing your team any favor. It was also not uncommon to see that the logic was so complex to join that it will require building and maintaining a lookup table to just cross-referencing these logs. And also what happened to the metric accuracy when you cannot reliably cross-referencing these logs. Instead of stitching logs together with this messy logic, what we really want is a unified, standardized join key. So what did we do? Almost everyone in this room understands that storage is always cheaper than the compute. If adding extra data to your logs can simplify your system, do it. Your finance team would appreciate that. With that in mind, we create this concept called analytic context that can be reused by all the services. Any contextual data, such as the detail of the job, the workspace, the cluster, would be automatically logged by the logging framework. Now the product team would only need to worry about logging tags associated with their own services. Let's see what this will look like. In the same example of user triggering a workflow, the job service emits logs. The job service logs the workload ID as job 123. Instead of the product team having to worry about persist that context, the logging framework is responsible for propagation this context across microservices and persist that context in every single log message. Here, the workload ID is logged in every product services. It is important to know that the analytic context must be set at the right granularity. For instance, simply set the workspace ID in the context provide little to no information. It must be set at the granularity that people want to do analytic at. At Databricks, typically this is every time a user triggering a workflow. By propagating and logging the universal analytic context, we enabled a new way to correlate logs across all the product services. Now, regardless of which service generates that logs, we can easily trace every event related to a single workflow, end to end, using a single standardized format. This not only streamlined our business logic, but also dramatically reduced the time spent on debugging, analysis, and cross-team investigation. This was a risky change that took a lot of testing to roll out, but in the end, the savings were clear. Tremendous cost saving and huge improvement in the operational uptime. In addition, there was a drastic improvement in the accuracy of those reported metrics. This can be credited to the replacement of heuristic logic with this standardized join key. The explicit workload tagging enables us to cross-reference accurately with those logs. This looks great, and to be honest, this would have been a decent place to just leave the pipeline at. The destination goal table was by far the most popular table at Databricks. And after all, it could answer any combination of adoption metrics, no matter the product or the product features. But what did it actually take for a product team to onboard the new metrics to this most popular table? Well, here is what the onboarding process really looked like. It starts with the product team filing a ticket. The data engineer will sit down with the product manager to dig into the requirements. Then the data team would collect all the requests and pick the most important 3 to 5 to prioritize. Then came another interview, this time with the product engineer to figure out if the necessary logging were in place. If so, the data engineer will hunt through over 60 files to add the new code. Then we will run intensive tests to make sure that nothing else breaks. We launch this change, we backfill the data. This process requires a lot of handoff and back and forth. The time from the product launch to actionable insights, it's about a quarter. This goal table was our North Star, the single source of truth for adoption metrics, no matter the products or the product features. But Databricks was expanding very fast. New dimensions and new products were coming from every direction. Organic growth, mergers, and acquisition. Every new product, every new team meant a new metrics that needed to be landed in this table. Whenever a metrics was missing, people consider it as a data quality issue, and all eyes turned to data team to fix it. We became the bottleneck. And here's the reality. Despite all the demand, we could only put at most 1.5 engineer for this onboarding process at any given time. Keeping pace with the company's explosive growth was a constant challenge. Beyond that, owning this goal table made us the omniscient engineer. We understand every product inside out and how every feature was measured. But that omniscience was dangerous. The whole company depended on 1 or 2 engineers to understand how every product worked. If that person was out or just for vacation, the entire onboarding process could freeze. The risk of being single point of failure had never been so real. And as a bonus, our omniscient engineer got another job title, Senior Slack Data Responder. Between maintaining this goal table, shipping new feature, and onboarding new metrics, they will also expect to have answer for every single data question anyone asks, no matter how random. If you are in a data team, you know the feeling. Someone comes to you, pings you on Slack with a question that you have never even thought about before, but somehow you are expected to know the answer. What we had at this point was a very pretty house of cards. People loved using it, but it came with big risk. As things became more complex, adding new metrics became increasingly dangerous. A single mistake, like an incorrect join or logic error, could break metrics everywhere. And what if the product team suddenly changed the way they log data? The whole house could collapse, since the product team didn't know how their logs fed into our metrics. Any change put data quality at risk. Soon, it became clear to the team that in the current model, it will require an army of engineers to maintain and update the pipeline. And here's the kicker. Even with all those engineers, our metrics will still be fragile and our definition would still fall out of sync. Why? Because the ownership and the incentive were still misaligned. We had to make a platform. The platform had to be self-service. We had to federate the ownership. So how did we get there? I will turn it over to Rohit for the best part of this talk.
Thank you, Neo. All right. So what does it mean to be self-service? For one, teams should be able to onboard metrics with little to no intervention from the data team. Second, it should be easy for teams to onboard these metrics. Finally, it should be possible for stakeholders to discover these metrics, look up their definition, and find out exactly which team to ask questions to instead of bothering me. What does it mean to be federated? Like any good system design, there are functional and non-functional considerations. Functionally, we would want the ownership and definition of these metrics to be federated to the product teams. In an ideal world, you also want to be able to capture the costs of evaluating these metrics and assign it back to the individual product teams. However, there are non-functional considerations as well. Onboarding a new metric should not break any existing metric definitions. That is, the metrics should be isolated and self-contained. There should be correctness guarantees. The platform should be able to scale horizontally as more metrics are onboarded without compromising on job or SLAs. As a platform, it is also our responsibility to ensure that teams cannot onboard arbitrarily complex metric logic that can stall the entire pipeline. There are a number of other considerations as well, like how do you handle backfills for a newly launched metric? We won't have time to go into all of this today, but we'll see how adopting a platform mindset will help us hyperscale. The first step was to make it modular. Instead of a PySpark notebook or Scala notebook or a Perl notebook evaluating n arbitrary metrics, each metric definition was encapsulated in a separate file. Each product team would then own one of these metric files, and product teams could add more files in a self-service fashion. Let's take a closer look at what one of these files looks like. To keep things modular and safe, we built a config-driven interface, essentially a structured YAML contract that all metric definitions must follow. Each file starts by declaring the name of the metric. In this case, is serverless. Teams can optionally provide a detailed description field, which comes really handy if you plan to later layer on LLM capabilities. Imagine going into the Databricks Genie space and asking the question, hey Genie, can you tell me the total number of DBUs associated with SQL queries scheduled using the job service? Break that down by serverless and not serverless. Oh, and only count jobs that are processed at least 30 gigabytes of data. Miranda would be so happy. Next, we define the source table. In this case, main.cluster events. We also define fields like date call and the workload ID call, which tells the parser how to extract all these columns from the table. Next, let's look at the feature definition. This is where we specify exactly how the metric is calculated. In this example, it's a simple Boolean aggregation. Select bool underscore or of the isServerless tag from the cluster events table, where the operation is cluster initialization. The structure here is very intentional. We use specific fields like select, from, and where. This isn't just for tidiness, it is a crucial design choice. Teams can't write arbitrary SQL, and that constraint is key. It is the only thing standing between you and the eager intern onboarding a metric definition that cross-joins 10 different tables. Great. Now that we understand how the metric is evaluated, let's take a quick second to talk about the engine. The engine is written exactly once and is thoroughly unit tested. And as such, adding new metric definitions can never break existing metric definitions. Finally, we have the ownership section, aka the don't bother me section. This is where fields like data scientist owner and eng team owner are clearly defined. If you have questions about the isServerless metric, you know exactly who to reach out to. The eng cluster controls team for product-related questions, or neo.ni@databricks.com for complex data science questions. This ownership model puts responsibility into the hands of the teams that understand their data best. It reduces ambiguity, streamlines communication, and empowers teams to own their metrics end to end. Finally, the Feature Explorer can be used by anyone at the company to discover all the metrics that are available, figure out who to redirect questions to, look up the definition in source code, and look up the SQL definition of the same. In addition to offering users a clear and structured way to define metrics, we provide an onboarding notebook. Here, users can experiment with feature definitions and preview the resulting insights in terms of dollars, DBUs, or whatever other metric they might like. This hands-on environment helps teams validate the accuracy of the metrics and build metric definitions that meet their specific business needs. All right, now that we understand the high-level interfaces, let's take a peek under the hood, a 10,000-foot overview, if you will. It all starts with the metric configs, which are defined in YAML. The config parser validates the configurations to make sure that they're correctly formatted and adhere to our interface specifications. Then comes the CI stage. This is where we run rigorous unit tests and integration tests, such as, does the config evaluate to a valid SQL? Were all the columns and tables referenced in the configuration existing in the metastore, or did they make typos? Once these tests pass and the PR is merged, the deployment engine kicks in to intelligently create as many jobs and tasks in the orchestrator as necessary. What does it mean to intelligently create jobs? Given all the feature definitions, we have a few different options. On one end of the spectrum, we can create a really large job that evaluates all the metrics, but we have already seen the pitfalls of having a very large unit of failure. On the other end, we can evaluate each metric in its own job. However, imagine the scenario where you have 7 metrics sourced from the same table. You now have to parse the table 7 times in 7 different jobs. That's a little bit like sending each member of your family in a separate Uber to the airport. Since we use the strict interface, we can do something a little more intelligent. We can easily figure out all the metric definitions that can be evaluated in a single pass of the table, and we just have to dynamically create one job for each set of metrics that can be evaluated in a single pass of the table. All right, let's take a look at what the onboarding process looks like now. Remember the arduous quarter-long process? Look at it now. One key improvement you would have seen is that only the product team is involved. There is no data team anymore. First, they create a config file. Next, they use our onboarding notebook to test and validate their metric definition. Make sure that it meets their business needs. Finally, they create a pull request and merge their changes into the system. And just like that, the metric is live, ready to generate insights. It's a dramatic shift from a quarter down to a single day. This slide encapsulates the achievements we made so far. Since launch, we scaled from 100 metrics to over 1,200, demonstrating its broad applicability and showcasing the platform's ability to grow with our needs. Thanks to metric isolation, our pipeline uptime has gone up from a precarious 97.5% to a robust 99.9%. Most impressively, we slashed the time to onboard a metric from an entire quarter down to a business day, fundamentally changing how quickly we can react to business needs. And we were able to do this with just one data engineering resource. All right, this is a great place to end the journey. Product teams that understand their features and the logging are in charge of metric definitions and their upkeep. The data team, which knows how to build robust platforms that scale, is in charge of the same. The incentives and core expertises are aligned. But this is where the exciting part begins. You can now begin to add functionality that is written once and can be leveraged by anyone on the platform. Let's look at a few examples. We provide anomaly detection, forecasting, and explainability as a service so that we have an automated way of finding out when things go wrong, when it'll go wrong next, and which in turn to blame when it does. We provide dozens of CAN metrics, like daily active users, weekly active users, revenue, out of the box for all the teams onboarding product instrumentation onto the platform. These aren't just nice to haves. They're key differentiators of a platform. We now have an ecosystem where we can author features once and benefit the entire organization. So let's recap and see why the platform model benefits every persona at your organization. Each team onboards metrics through simple, isolated configs. The metric engine is written exactly once and thoroughly unit tested, meaning that new metrics cannot break existing ones. Behind the scenes, the platform is able to stitch together the lifecycle of the workload using the analytics context. The intelligent optimizer is able to go through all the definitions, figure out exactly which metrics can be evaluated in a single pass of a table, and calculate all of them in one job. All teams, even with this minimal config, get dozens of metrics like daily active users, DBUs, dollars for free. The data engineering team is now focused on just add best practices. And the data engineering team can finally start building practices that meet with their core expertise. Management is happy because they are not spending all their time interviewing new candidates. Product teams and PMs are happy because they are no longer bottlenecked by the data team and they have reliable metrics. The data team is happy because they can finally put their ML Coursera certificate to use instead of talking to PMs and responding in questions on Slack. And the org is happy because now we have a model and processes that scale with the company. So that is our journey from a single pipeline held together by tribal knowledge to a robust, federated platform for scaling and ownership. We didn't need an army of engineers to get here. It took just one and the right mindset. If your organization is feeling the weight of rapid growth, siloed metrics, or data team bottlenecks, now is the time to shift your mindset. Stop building pipelines, build platforms. Thank you.